So, hi everyone, and welcome to this deep dive presentation of our in-memory technology. My name is Henning Andersen, and I'm the Chief Architect at Stibo Systems. A few words of myself. I've spent the last 20 years working for Stibo Systems. I've been developing software for more than 30 years. I've been the technical lead on many projects at Stibo, like migrating from our old C++ to a Java platform with a heavy focus on performance and scalability, establishing a component platform, allowing us to deploy components individually to our platform, and lately being the technical lead on our in-memory component, the topic of today. So who is Stibo Systems? We are a worldwide company with 18 offices worldwide. We have a global headquarters in Aarhus, Denmark, where I'm also located. We have more than 500 employees and have more than 250 customers. And these are some of our customers, and I'm sure you all recognize one or two logos up here. We operate in different verticals like retail, distribution, manufacturing, and travel hospitality. And while Stibo Systems may not evoke a lot to you, I'm sure most of you have heard of the industry analyst firm Gartner, and for 3 years in a row, they've ranked us a leader in our space, and they've communicated that we are now third in market share right after SAP and Oracle. Our primary product step is a master data management system. It helps our customers acquire, manage, and publish their master data. We operate in different domains like the product domain, customer domain, location domain. And managing the data can be many things like data maintenance, matching and linking, establishing the data, the quality of the data. We have a built-in workflow engine and much more. And we integrate to a variety of third-party systems like ERP systems, CRM systems, and business intelligence systems. And the customer can then distribute the data to various downstream systems like websites, point-of-sale kiosks, mobile devices, etc. And for all of these things, well, there's a lot of different activities going on actually, and for all of these things, we really need great performance, which is why we were looking into the in-memory technology. So this kind of illustrates our vision for integrating in-memory into our system step. On the left, we have our traditional system with a database at the bottom, a cluster of application servers, and some UIs and external API traffic on top of that. And on the right, we have the system with an embedded in-memory database embedded into our Java application server. And since we're Java shop, we need to go off heap, since otherwise the garbage collector would go crazy. And if we look at just the minor detail symbolized by the arrow between the application servers and the database, so we see that the arrow primarily goes down from the system within memory, meaning we still do all writes directly to our database, but we intend to serve all reads directly from the in-memory database mirror. And through that, we hope to gain some speed-ups. Let's look at what results we got out of it. Here we have some benchmark results where the red bars is with our normal system, and the yellow bars is with in-memory enabled. And as we can see, especially for the complex searches we have done for a large retailer, we see a more than a 100 times speed up, whereas for various other scenarios, we see a good, decent 3 to 5 times speed up. So naturally, going into this, our first thought was to find a third-party vendor of in-memory technology that we could use. And we set up some requirements for that. First of all, we naturally need great performance. That's the whole purpose of the exercise. But we also need compact memory layout. Since we are a master data management system, we have a lot of very granular data to store. And compact memory layout has two factors to it. It has both the actual ability to compress the data somewhat, like do we need to store a date in 8 bytes, or can we do with just 4 bytes since we only need second granularity? Do we have that flexibility? And also it's the per entry overhead. So you have 10 billion entries in your in-memory system. A 100-byte overhead would mean you're spending a whole terabyte just on overhead. We need to do lookups by key, meaning we need a traditional key value store. And we need to be able to do complex querying on the values in that key value store. And to do that, we'll need some kind of indexing. It has to also be friendly to our existing architecture. We have 3.5 million lines of code. We spend more than 200 man-years on this. We cannot just rewrite everything to fit some in-memory technology. So we prefer some kind of incremental process in order to get into the in-memory world. And finally, we need fast startup. And what we envision is that when booting the system initially, we'll simply read out all the data from the database into the in-memory mirror. And to do that, we may need some kind of faster way to get the data into the in-memory mirror. So we looked at the third-party products out there, and we found that all the products we examined failed in one or more of these aspects. Some of them were really not friendly to our architecture. Some of them have pretty protective APIs, and by that I mean they would not allow us to just go into the off-heap data and just grab the 1 byte that we need. We would need to get a full copy out of the entire data, meaning they would deserialize the entry out to us. That's a whole lot of overhead to copy data out, just to look at a single field of it. And also it creates problems for the garbage collector. It creates a lot of work for the garbage collector. The compact memory layout, we would see typically that they had a too large per entry overhead. And also some of them have different key value stores and query engines. They're sometimes separated. And again, that replicates data over to the query engine. And also it means that the consistency between the two is hard to maintain. So eventually we decided we need something more dedicated, maybe simpler, and really, really fast. That's what we were going for. So these are some of our thoughts on that. So we thought if we could make something very simple, we could probably also make it perform well. So about multi-version concurrency control, we figured we would use immutability. And what we mean by that is that if you have an entry in the database, rather than go and update that in place, we would create a new entry overshadowing the existing entry. And we believe that if we have immutable data, right, doing weight-free index scans, where no matter what occurs on the platform of inserts and deletes and updates, doing weight-free index scans means that they will actually continue no matter what write activity occurs. We believe if things is immutable, well, that's easy, right? Also, using heavy code generation and custom APIs, we believe we could gain direct access into the actual off-heap memory to just pull out the few bytes that we need whenever we need to pull out data. So essentially, what we were after was to get a little closer to the underlying language of the platform. And here we're looking at one of the instructions we do when we compare strings during inserts into our string indexes. All right, so let's dig into the details of this. So we actually start with a basic hash table using closed addressing. And this is just real quick going through that. A hash table is built up of a bucket table. And in each bucket, you'll have one or more entries. 0 or more entries actually, and here we have the key K1 and the value 10 in this second bucket of this hash table. And we can naturally have more values in this, like here we have the key K3 value 20, and we can have a third value, key K4, which would collide. It would use the same bucket, meaning what we'll do is we'll link these entries together using the same bucket. This is basic hash table stuff, right? So here we have 3 entries in this hash table. So let's try and add some multi-version concurrency to this hash table. And what we'll do here is we'll add 2 controlling data structures to the right here. The first is the transaction table, having a transaction ID, which is basically a unique ID, allowing us to communicate about this transaction. And it has a TSN, the transaction sequence number, which is kind of the time of our database. It's a monotonically increasing number that the whole cluster of application servers agrees upon. It's much like the Oracle system change number, if that sounds familiar to you. And using that, we can do some good stuff. And we'll have a single atomic long, the published TSN, which is basically the number, the time that any reader would come into the system, would take this published TSN and use that number to then read through the entire memory database, and thereby creating a snapshot of the entire database. So, but before we dig into that, let's just look at the different phases of the transaction, or maybe I should really say of a commit. Because the transaction has already been going on for a while, collecting all the data that we need to change and post into the database and the in-memory mirror. So if we look at it here, we have on the left, we have 4 servers in this cluster. We designate one of them as the leader, and naturally the system will re-elect the leader if a crash occurs. And on the right, we have the various phases of a commit. So first we do the prepare phase, in which we'll allocate the memory structures allocate and populate the memory structures for the new entries. And the transaction owning node will send out a message to the other servers in the cluster with the payload with all the entries that needs to be updated in the memory database. All right, having done that, the transactions owning node will go to the commit phase, where we'll commit the data to the database, and if that fails, we'll move to abort. We won't cover that here. But if it succeeds, it will send a message to the leader saying, well, this transaction committed successfully. And now the leader is responsible for completing the rest of this transaction. Next up is the finish phase, which we'll cover in much more detail a little later. which is basically about hooking all the things up. What the leader does is it pulls a new transaction sequence number from an atomic long, it simply increments an atomic long, and thereby pulling a new transaction sequence number, which is sent out to all the other nodes in the cluster, signaling to them they also need to finish this transaction. Once they're done that, they'll send an acknowledge message back to the leader naturally, and when that's done, the leader will start the publish phase, in which we will send out the publish message to all the other servers in the cluster saying TSN3 is now published. And from this time on, this transaction can be seen by other readers. Before this time, naturally, this transaction is, the content of that is invisible to readers. And we lost the signal. Oh. And finally, there's the vacuum, which is basically some cleanup that we do, and we'll cover that in more detail a little later. Abort and commit, we'll not cover that since it's the in-memory part that's relevant here. So let's look at updating into a multi-version consistent hash table. And let's say we want to do put k1,15, meaning we want to update the value for the key k1 to be the value 15. First, we'll do the prepare phase, in which we'll allocate the new memory structure necessary for this entry. We'll populate it with the key and the value. And we'll allocate an entry in our transaction table, giving you a unique ID. And we'll have a pointer to the entries of the transaction. Actually, there could be thousands of entries in this transaction. For simplicity, we'll show just one here. Next is the finish phase, in which the leader will pull a new TSN simply by doing an atomic increment of its atomic long for the TSN sequence, and it will be assigned to the transaction. We will move on to assign that to the entries of this transaction, so that they all know which TSN they belong to. And we'll then link this new entry to its previous version, meaning it's the time going back in time. It will link it to its previous version of the same of the entry for the same key. And finally, we'll update the bucket table to point to the new entry. And that's the first 4 steps of the finish phase. There's a 5th sub-step, which is basically to do with indexing. And we'll cover that in more detail a little later. But now let's look at the state of things. So we didn't actually publish this yet. The published TSN is still 2. So a reader comes along in TSN2 wanting to look up the key K1. So what will the reader do? He'll look up the right entry in the bucket table, hashing the key modulo table size. Follow the pointer down and look at the TSN down here. The TSN is free. The reader's TSN2, it's too new data for this reader. The rule is that the entry of the TSN has to less than or equal to the reader's TSN. So what we'll do is we'll follow the previous pointer backwards, find the old entry, and we'll look at this and we'll say, well, this TSN is good. The result of that lookup, key K1, is the entry with the value 10. I forgot to say before, naturally, there can be many more fields than just one field in such an entry. There can be many fields in here. But now we got that entry out. All right, so let's move on to the publish phase, in which we'll simply update the published TSN. It's just one atomic update of this long, saying now the published TSN is free. And since it's an atomic one, it's an update that covers all the entries in one go, right? So a reader comes along, now able to see TSN free and looking up the key K1. So let's see how that goes. Well, we'll look it up in the bucket table, find the TSN is free, that's perfect. So the result of that lookup, in this case, is the entry with the value 15. And that actually makes this a multi-versioned hash table. And since we're doing this for all the entries of the hash table, it's also consistent across the entire hash table. So that's really all there was to creating a multi-version consistent hash table. So let's move on to something else. Let's move on to indexing. So in order to do efficient querying, we need indexes against our values. We want to do queries against the values of our data store. And in order to do that, we need indexing. And in the following, I'll share just one index per entry, but naturally there can be multiple indexes per entry. And we use something called skip lists for that. And let's just have a quick intro to what a skip list is. Well, a skip list is built up of multiple levels. At its lowest level, a skip list is basically a linked list with a head entry and some different entries in it with pointers between them. It's actually an ordered skip list, which is important to us here. Sorry, it's an ordered linked list, that's what I meant to say. So a skip list then has builds several levels on top of this. And it's built such that approximately half the entries have a height of more than 2, and approximately then half of those again have a height of more than 3, and so forth. So that we end up with the highest entry in the skip list having a height of approximately log 2 of n. So say we had 1 billion entries in this skip list, we would then have a height of 30. The head naturally has to have minimum the same height as the highest entry of the skip list. So with that in place, let's just try and search for some stuff in the skip list. So let's say we want to find the value 30. We'll start at the head entry at the topmost level. We'll just peek forward to the next entry at that level, and we'll look at the value for it and compare it to the value we want to find. In this case, we're looking for the value 30. So comparing to 40, well, if we moved that, we would have gone too far. So instead, we go down on the head, and we peek forward again. The value 20, well, that's fine. We can go there. So we'll jump to 20. And we'll go down and peek forward again, and the next value is 30, we can go there. And that's how you search in the skip list, right? You either go right or you go down every time you do a search. And like what we saw here was that we actually skipped the value 10. We never really got to the value 10, which is why it's called a skip list, because you skip a lot of entries, especially when the list gets large. And we're doing this in log 2 of n operations. So let's look at inserting into a skip list. Let's say we want to insert the value 15. Well, and here's one of the interesting things about skip list. We'll pick a random height for it. And one way to think of picking a random height is to simply toss a coin, and every time it says heads, you will add another entry, and when it says tail, you stop. So you will pick a random height. In this case, we hit head once, and then we hit tail. So the height got to be 2 for this entry. And why is that interesting? Well, if you have a lot of concurrent inserters going on, picking a random height means they don't have to communicate. They don't have to balance to ensure that it's a balanced tree or skip list or anything. And statistically, this will become a balanced skip list by doing it randomly. So that's one of the reasons why skip list is good to make weight-free and log-free algorithms. So we'll find the right place to insert it using that search find algorithm that we saw before. So we want to insert this between 10 and 20. And we'll just start by linking to the next entry. And then we'll do one atomic update from the previous entry to this entry. And we'll do the same bottom up at each level. And this time it's from the head to the new entry. And finally, well, we got this inserted, and now we preserve the skip list and the ordering and all that. So with skip lists in place, let's look at combining that with the multi-version concurrent hash set that we have. And here we have the same view that we had before, except we went one step backward. We didn't actually publish this yet. If you look at the published TSN over there, it's still 2. We didn't update it to 3 yet, so that's where we are. So we'll do the 5th substep of finish, which is basically to update the index. And to do that, we'll just turn it upside down since it presents a little better that way. And if you look at the highlighted entry, well, you can see that it has actually the previous pointer backwards to the previous entry. There's 2 entries here with the key K1, which is the 2 different versions of this same entry. But if you look at the index pointers, they're bypassing this because we didn't link it in yet, and that's basically the job of the 5th phase, and we won't go through that in detail now because we did that just on the previous slide where we inserted into the skip list. So we'll simply just ensure that this entry gets inserted into this index. So let's say we want to find some values in this index. We want to find all the entries with a value between 12 and 25 using TSN2. So a reader comes along, we didn't publish it yet, comes along using TSN2 and wanting to find this value. So what do we do? Well, we use the find algorithm that we saw before. Eventually, we'll get to the value 15. We'll look at the TSN. Again, this is too big a TSN, so this entry will not be part of that index game. Instead, we'll jump forward to the next entry. 20 is still within the range. So we'll look at the TSN. TSN is 2, that's good. So this one entry is the only entry that comes out of this index scanner finding values between 12 and 25. All right, so let's say we actually did publish this. So now we are doing a reader that just says TSN3 at the top of here. So a reader comes along and wanting to find the same stuff but using TSN3. Well, in this case, both entries will apply. Both the values, the entry with the value 15 and the entry with the value 20 will apply. And both entries will be part of the result for this. And that actually makes this a multi-versioned index, right? A multi-versioned index using skip lists. So now we have a multi-versioned index, and we have a multi-versioned hash table. That's pretty close to a whole in-memory solution, right? And naturally, there's still only one value here. This is, of course, complete entries with a lot of different fields in them. So let's just have a quick summary and a few details on the Lockfree insertions here. We use the compare and swap operation to ensure that there's only one win of the operation. The compare and swap operation is a CPU level instruction that ensures that only one of the, if there's concurrent modifications, only one of them wins. So let's see how that could go. Let's say we have 15, just like before. We want to insert this into the skip list. Along comes a new thread, another thread wanting to insert the value 17. And these are kind of competing for the same space between 10 and 20, so we need some kind of coordination here. They'll both link to 20, let's say that, and then at the very same time, precisely the same time, they want to hook themselves up to be after 10. And since we're using the compare and swap operation, one of them will succeed, the other one will fail. And here, the link to 15 succeeded, and the link to 17 failed. 17 will retry it a little later. We'll see that in a moment. But I just wanted to, at this stage, also look at the state of this skip list right now. Actually, even in this state, we can do wait-free index scans on this. This is still a valid skip list to do index scans on. So this is one of the interesting things as well, that even at this half-linked state, you can actually full-speed index scan this without waiting for any inserters to occur. We're doing wait-free index scans on this thing here. And one of the reasons we can do that is because we're doing it bottom-up. If we did it top-down, we would not be able to do that. So let's just say that 15 actually completes its stuff, and then eventually 17 will do a retry. So when it fails, it has to do a retry from scratch, meaning it has to find the new place where it belongs. It now finds that it belongs after 15, so it will simply link itself to be after 15, and we got the new version of this in place with the right order of things in the skip list. One little detail, we'll cover vacuum in a moment, which is the cleanup process. But in order to ensure lock freedom of insertion, the inserters has to help vacuum, meaning that if there's some cleanup going on that's marked the entries for cleanup, the insertion will actually link will actually help vacuum clean up this entry, because otherwise, if we had to wait for vacuum to complete this operation, it would not be a lock-free algorithm, because that's the definition of a lock-free algorithm, is that no matter what it can continue, it may have to retry, in principle, an indefinite amount of times, but it can never sit and wait. Then it wouldn't be a lock-free. And we want it to be lock-free, so therefore we made it so that it helps vacuum. And actually, if you look at the Java concurrent skip list map, it does the exact same thing for insertion and deletions. So let's talk about vacuum and cleanup. So if we look at the highlighted section here, we can see that we actually have 2 entries for the key K1. So to some extent, right, we're using twice as much memory for that key than we should, at least in the long run. And if we just continue down that road, right, we would run out of memory eventually. So we're doing something we call epoch-based deferred reclamation here. And to control that, we add a third controlling data structure called the snapshot registry. And what that contains is a list of all the readers that are inside the in-memory database at this time. So here we register the reader by thread, and we register which TSN it uses, and then we register the epoch value. And the epoch value is kind of the time of the snapshot registry. And we trigger an epoch change, and vacuum triggers the epoch change when necessary. So let's see how that goes. So we want to do vacuum, but actually first vacuum has to wait, because that reader wants to use TSN2. So what we need to clean up is the old version for the key K1, but we cannot clean that up yet, because then he wouldn't be able to answer lookups of key K1 or do index scans for it. So we'll have to wait until that reader terminates. Eventually that reader will be done doing whatever it does, and it will be removed from this snapshot registry. Now vacuum can move to phase 1, which is basically index related. It will go to the index and it will unlink the entry from the index. There's a few more steps to it in detail with marking entry stat and stuff. I won't cover that here. But its basic job is just to unlink the entry from the index. So now we've done phase 1. And then we'll have to do an epoch wait. And what we'll do here is we'll trigger an epoch change, meaning that new threads coming in will now get epoch 18. And then we'll wait until everyone in epoch 17 are done. A new thread could come along, it will get epoch 18. And I forgot to say, so why do we need to do this? Why do we need to wait here? Well, this thread started in epoch 17. So even though we unlinked it from the index up here, that thread may actually have a pointer to that entry in one of its registers or local variables or whatever. And if we deallocate that entry right now, there's a risk of segmentation fault, right? And we definitely don't want segmentation faults. So we'll wait for that thread to finish. So another thread comes along, gets epoch 18. Eventually, this thread dies. It's completed its read operation, and it will be removed from the snapshot registry. And now we're actually done waiting. So vacuum can move to phase 2. But why is it safe now? Well, since we updated the index, we unlinked the entry from the index first, before we triggered the epoch change. We know for a fact that reader down there, there's no way it can have a pointer to that entry in one of its registers, the local variables. There's just no way that it can have it. So we can safely move to vacuum phase 2 now, which is basically to go find the entry, deallocate the memory for it, and that's it. So we did the reclamation of memory for this entry. We are now done with the transaction. We can remove the transaction from the transaction table. And that kind of completes the entire flow of this commit, of all the phases of this commit, so that we are now back to where we were to begin with. So a quick summary of what we've seen. We've seen a multi-versioned consistent hash map. We've seen maps and indexes that are both under multi-version concurrency control. And they're under the very same multi-version concurrency control, meaning we can mix and match key value store lookups with queries, and we can do multiple queries on the same snapshots. We've seen index scans that are wait-free, meaning they'll run full speed, no matter what activity goes on the indexes, inserts, updates, deletes. The index scans will continue to run, no matter what. So there's nothing stopping our readers. Readers will always run. And we've also seen, well, a fairly simple, right? You go down or you go right. That's what you do. So it's a fairly simple algorithm, meaning it's going to be fairly fast as well. We've seen insert, update, deletes that are lock-free. And, well, in fact, we only saw an update that is lock-free. I guess inserts are obvious. We already saw how to do the inserts there. And for deletions, well, the solution is to simply insert a tombstone. So that covers deletions as well. And we've seen automated reclamation of storage. That vacuum process we talked about runs in a separate thread, meaning it's automated and runs concurrently with the application. So let's move on to talking about the actual API for getting to data. And we've created what we think is an efficient and still safe API. So this is a short example of some code that could be running inside our application. So. And the first thing it does, this is a reader, and the first thing it does is it calls transaction manager.read, passing it a lambda expression. And what the transaction manager will do in response to this is to create a snapshot for the current TSN, the currently published TSN. And it's just, snapshot is just an encapsulation of that underlying TSN. Also, it will register this transaction into the snapshot registry that we saw before, such that the vacuum process is safe to use. Next, in this example, it will call snapshot.query, which does a query against the indexes. We'll query for all products with an ID in the range IMC to Stibo. So any product that has an ID in that range will come out of this query. We'll loop all the results of that query. And for each of them, we'll call queries rated.entry here, which returns a cache entry to us. So a cache entry is not a copy of the entry. It's just a pointer to the entry. Actually, it's what we'll call a flyweight object, right? So it's the same cache entry you'll get back for every iteration of this loop, which allows us to go in and get some stuff out. And that's what we'll do in step 4. Here we'll call entry.long value, and we'll pass it a method lambda expression here. And what that does, This is that it goes directly into the off-heap storage and just pulls out the one long that we have in there and returns it into the application here. Typically, that would be in a CPU register, meaning it's going to be pretty efficient. And using that, we can then go to call the get operation on the snapshot, which is basically where we're using the key value store kind of lookup. So now we're mixing queries with key value store lookups. And again, we'll get a cache entry back, not a copy of the entry, but a pointer to the entry. And we can then do various stuff based on that as well. And one interesting thing here is that there's no way that object type will not exist, because that's a fundamental fact about our system, that a product always has an object type. And there's just no way it cannot exist. So we're absolutely sure it exists since we're getting it out of the same consistent snapshot. So a few facts on this. We're not doing any object copies, meaning the garbage collector will have it a little easy. Actually, if you look at that loop, the while loop, there's actually no allocation going on in there. It's allocation free, that loop. There's nothing going on in there for allocation, meaning the garbage collector can take a well-deserved break, actually. And it's very efficient access since we're doing this entry long value. Just take out the one long and return that. It's very efficient. Also, one interesting fact, since it's so simple, so to speak, often the JVM can inline this entire query, or at least the entire loop, to one native method. And that's also pretty important, because it means the JVM can use all the tricks it has in its book, register allocations and reordering of stuff to make it very, very efficient. And that comes out of the simplicity that we have. So rounding off a little here. So suppose some of you want to go and do it yourself as well. There's some useful learning that I think you should go through. Like the memory model of the platform you're on. It's really important to know that memory model. And please notice that, for instance, Java memory model is significantly different from C++. Among others, the keyword volatile has a different semantics. Also, the compare and swap operations are pretty important to know about. How do they work? I also suggest to get to learn some assembly. Well, I wouldn't suggest you write assembly, but being able to disassemble from the JVM can actually disassemble what code it generates. Being able to do that and look at the very tight loops you have and the very hot methods you have, you'll find some eye openers in there that will make you change your code so that it runs faster. Also, have a look at the CPU memory architecture. Nowadays, CPUs have a sophisticated memory caching hierarchy. And instructions that sometimes take one clock cycle because it's in the level 1 cache will sometimes take hundreds of clock cycles because it has to go to DRAM. About wait-free and lock-free algorithms, it's a good way to think about it is to think about states and thinking about state transitions. So when you're doing compare and swap operations through your algorithm, you have to think about compare and swap operation as a state transition. Well, rather than think about it as assignments in an imperative language, you should think about it now go from state A to state B. This is really important to think about all the states your things can be in, your model can be in, and then ensure that they're all right. So try to formally prove it right. It can be really hard, but at least try to stand up in front of your colleagues explaining this is perfect, this is what I did, and make them shoot at you, and you convince them, right? Also remember deletions. We saw that deletions are often the most tricky part, and we saw that with insertion having to help vacuum. So thinking out this solution for insertion is probably not it's not the whole story. It's probably not even half the story. It may just be the easy part that you've gone through. And also sometimes you'll get into a situation where you've got two pieces of code, and there's a slight chance that if it turns this way, right, that something could go wrong. But I mean, how likely is it? Well, don't even think about it. It will happen. That's going to cause you issues. Also, some questions for third-party in-memory vendors that I think are relevant. Like, do they allow direct access to data or only access to copies of data? And direct access to individual fields in entry, or do you need to take out more data than you actually need? Or can you just go and grab the stuff you really need? Also, these products will have different consistency guarantees. Some will be eventually consistent, some will have stronger consistency guarantees, and that's naturally okay. But within those consistency models that they operate with, can you mix and match queries and key value store kind of lookups? Also, will index scans in queries about logging, will they require logs, right? Because even though if you're using shared logs to do index scans, If there's a lot of write activity, well, you're not doing any reads anymore because then there'll be mutually exclusive locks from the index insertions. And also, if you have index inserts requiring locks, well, you will not be able to do multiple inserts at the same time. All depends on the use case you have and how your data flow is, which of these are interesting. The same goes for map, get, put operations. Also about the memory overhead per entry, it's very important to know this because it can limit how much data you can store in a single node, right? So actually, in our case, we're down to around between 50 and 60 bytes of overhead per entry. We'll cut that down a little more through coming releases, but that's pretty much better than what we saw in the products we examined. Also, the memory overhead per index per entry is relevant. Especially if you have products where they store the query engine separately, there'll be some replication of data going on, meaning it's going to be quite a lot of extra overhead for the indexing. In our case, we have an overhead per index per entry of 12 bytes, which is pretty good, I think. Memory fragmentation, well, I'm not sure I need to mention that, but of course you need to avoid memory fragmentation because if you have uncontrolled memory fragmentation, eventually you will run out of memory. Page locking, you need to lock the pages in memory. I'm sure most products can do that. But of course, if the OS starts swapping out your in-memory mirror, it's no longer an in-memory mirror, right? It's a disk-based mirror. Also, you need to should use huge and large pages because if you have many gigabytes or terabytes of memory, the kernel will have a very large page table, and that's a big thing to manage in itself. And also the CPU has this translation look-aside buffer which will suffer if you don't use huge pages. So that's basically all I had to say today. So thank you very much for attending, and I think we have some time for questions. If there are any questions. All right.
Is there a source code for the data structures that you showed? Like, where could I find example implementations of that?
So the instruction.
The source code for the data structures.
No, this is a proprietary owned product. It's closed source. All right. Well, thank you very much. Oh, there's one more.
Did you publish any of your evaluations of the vendors that you were looking at?
No, we didn't.
Would that be something you'd be willing?
Well, not in this forum anyway, but you can naturally PM me or send me a message privately, and we can look into it. Yeah.
Yeah.
Sure.
I think it's an optimistic looking approach, but if there are a lot of conflict between the transactions, what do you change it to the explicit lock?
So if there's a conflict between transactions, how do we handle optimistic locking? Well, it's you can just go back a few slides. That's really down to where we start, right? Because find it here. As I mentioned, this was our vision, right? We still have the database at the bottom, and the database still does locking, and it does the optimistic lock checks for us, right? So that's a simplification that we have in our case that many of you may not have, but it simplified things for us because we wanted to still have the database at the bottom, and it means that we don't have to care too much about locking. We're still caring about locking, actually doing something we call early TSN check and pulling the TSN a little earlier than we otherwise would if there's overlaps of data, but that's all we do about it in memory-wise. Sure.
How are you doing the atomic operations across the cluster? Is that your own implementation as well?
Yeah, so the atomic operations across the cluster is basically what let me just find it here. That protocol that we had here, right? That's essentially what does the atomic operations, and in the end, the publish is what does the atomic publish of everything in one go.
So you implemented your own leader election?
Yeah, we did that. Yeah, it's a whole different story, the recovery part and the whole clustering. Yeah. Well, thank you very much.